I gave you an introduction to basic circuits, and we did a voltage divider, current divider, and we measured the power. And of course, our objective was to get the cybers out of the power measurement. And now let's keep going and get into the interesting kind of work that electronic devices can do, which is computational work. And we want to measure the computations because the secrets are inside the computations. There's not a lot of secret in the sound or something like that. Okay, so basically, in an electronic circuit, there are two kinds of components, and they're called passive and active devices. And the passive devices are devices which don't control what's going on with them. They're just on the path of the power. And the most common one is the resistor. A resistor just resists the current which is flowing through it, and so it really hates it, and some of them come out. And the other two are the inductor, the sleeve, the coil, and the capacitor. Now, the inductor, it actually looks like that, and what happens in that when current is going through it, it starts spinning, and it stores energy as it's spinning in a magnetic flux, and you can use this as a source of current. When you disconnect it from the current source, you can use this current again. The capacitor is two plates of conducting material with an insulator between them, and it's a source. It stores current. It stores potential. So you can create a voltage. You can store current in the capacitor, and when you disconnect it from the power supply, you can use the current for something else. Now, these devices, the passive devices, sometimes you put them there on purpose, and this is the course to talk about why. But sometimes it's just a matter of fact that every time you have a circle on your printed circuit board, you create an inductor, because this is how physics works. Every time you have two pieces of conducting wire which move together for some time, you create a capacitor. So these are the passive devices. So an inductor is a coil which stores current. So you pass a current through the coil, and then if you stop giving current, the coil will get this. It stores current, and then it will. What you use coil for an engine, for example, is a coil. You can use it for all sorts of other things. I don't want to go into this. Isn't the subject of this course. What do we need these devices for? So these are the passive devices. But what is more interesting for us is the active devices. And the definition of active device is a device that controls electricity with electricity. Electricity controls electricity. Basically, it does different things, not just passively, but also it has some kind of agency. And the most, I think, the simplest kind of active device which I can explain to you is the amplifier. So we all have amplifiers in our cars. Some of us have really big amplifiers, and then some of us have other things. But how does an amplifier work? So obviously you get some kind of weak audio signal coming in, and you get a very powerful audio signal coming out, right? And how does this work? It doesn't work with magic. What else do you have to provide to the amplifier? What else do we need? Yeah, we need to give power. So the amplifier has two inputs. It has a power supply, and it has this weak audio input. And outside comes the powerful audio output. And it's controlling, it's using this power supply to create this powerful output based on the weak input. So very, very useful device. And now a transistor, it's a very, very interesting component, and I'm going to spend a couple of minutes talking about transistors. Transistors can be used as amplifiers, but they can also be used as switches, and this is what I'm going to talk about in the course. And transistors are the building block of an integrated circuit. IC is an integrated circuit, which is a bunch of all of these transistors and also passive devices bunched together, and then you get like a chip with a lot of devices together. Now I want to talk about transistors in some detail. Now they were invented by George Transistor, and I don't know who did. I didn't write it down. Probably somewhere on Wikipedia. Um, but the most interesting kind of transistor, which is used in electrical circuits, is what is called the magneto-oxide silicon field effect transistor, or the MOSFET. And this is what I'm going to talk to you during this course. And this is all the transistor education you need to get to understand this course. So who is seeing this for the first time? Are you seeing this figure for the first time? Say yes. You already know how a MOSFET works. Say yes. Say no. If you don't know how it works, say, I forgot what was the question. Anyway, I'm going to explain what okay, let's do it. Should I explain what a MOSFET does? Should I explain? Okay, this is a better question. Okay, so I'm going to explain what a MOSFET does. Yeah. So a MOSFET is a transistor is built out of a semiconductor. A semiconductor, silicon is an example of a semiconductor. Well, what is a semiconductor? We know that there are things in the world which are conductors. For example, gold or copper, they're conductors. And we know there are things that are insulators. For example, glass. What is a semiconductor? It's something which is a conductor, but it's not doing a good job. What is a semiconductor? So a semiconductor is something which conducts. No, it's not only one way. It's some material that conducts sometimes. You can decide when does it conduct and when does it not. And how do we build a? Okay, yeah, if you're brave enough. How do you build a silicon-based semiconductor? So some of you know chemistry, some of you don't. I'm just going to say it again. The silicon atom is built out of three components. We have the neutrons, which I really don't care about. They're neutral, so I don't care about them. We have the protons, and the protons are very, very heavy, and they sit in the nucleus together with the neutrons. And we have the electrons. The electrons are negative, and they're very, very light, and they are arranged around the nucleus in what's called valence bands, right? Remember the valence bands? Like these circles. It's not actually circles. So the silicon transistor has several valence levels, and at the top level, how many electrons does it have? Does anybody know? I stare represent how many electrons does silicon have at its top valence level? Seriously? Okay, it's 4. It has 4 electrons in the top valence level, and there are other electrons below. And when you create a crystal of silicon, a lattice of silicon, each one of these 4 electrons connects in what is called a valence bond to another silicon atom, and you get a really, really nice lattice where the protons and the nuclei are in the middle, and the electrons are connected. And this is a very, very stable material, and the electrons are really, really happy where they are. And because they're very, very happy, the silicon, pure silicon, is actually not a very good conductor of electricity at all. Because you need to work very hard to get the electrons to move. And that's not a very good conductor. Now, there are 2 materials which are molecularly very similar to silicon, and they are boron and phosphorus. Now, boron is very similar to silicon, but it only has in its top valence level, instead of 4 electrons, it only has 3. And phosphorus is also very similar to silicon, but in its top valence level, it doesn't have 4 electrons, it has 5. So what you do when you want to create a semiconductor is you take the silicon and you dope it with one of these materials. You can dope it with boron, or you can dope it with phosphorus. You can also do other stuff. You can dope it with other materials. But if you have, for example, a silicon which is doped with boron, what happens here is that all of the silicon and silicons create this beautiful valence bond, but the boron material only has 3 electrons. So 3 of the directions of the boron are connected wonderfully to the silicon. And one of the directions, there is nothing connected on the other side. And what this nothing is called in Hebrew is called choronim. Sometimes it's called holes. It's like a desire to have an electron. And these holes are very, very not happy where they are. These holes really want an electron. They want to steal an electron somewhere else. And these holes are actually, they can travel from side to side, and you can conduct holes if you put boron. If you put phosphorus, the other way around happens. You put phosphorus. Phosphorus has 5 electrons, so 4 of them form a valence bond with the silicon around them, and the extra electron number 5, really is floating and doesn't have anywhere to go, and this electron really also is very free to travel. Now, again, there are the same amount of electrons and protons, so it's not charged, but the holes, they can travel, and the electrons can travel. So who is hearing this for the first time, the story about the electrons and the borons and the photons and the neutrons? Okay, great. So nobody can tell me if I'm getting it wrong. Wonderful. Yeah. So now I have a piece of doped material, so I can have either too many electrons if I put phosphorus, or not enough electrons. I have these holes if I put boron. But this material is electrically neutral. It's not charged because there's the same amount of electrons and protons. But now I put a piece of n-doped silicon next to a piece of p-doped silicon. Now remember, in the n, there are too many electrons. I hope I'm getting it right. Yeah. In the n, there are too many electrons. In the p, there are holes that really want electrons. Great. What happens now? As soon as I put these things, as soon as they bond them, all the electrons, the spare electrons from here, are going to run away to the other material and fill the holes there. So there's going to be a boundary layer between these two devices, between these two materials, where there are these strong silicon. There are four electrons to each atom, and again, current doesn't want to flow because the valence bonds are very good. So as soon as I create this, there is no current in the transistor. Now the transistor, if I try to pass current through the source and into the source and out through the drain, it won't be able to travel because it's called the depletion layer. It's just very satisfied as it is, and so current can't travel. What do you do in a MOSFET device? What you have here is an electrode. This is this brown thing, and this electrode isn't actually touching the silicon. There is a bit of glass insulator here. Silicon oxide is glass, now you know. But what I'm doing, if I want to change the status of this transistor, I am going to put a lot of electrons inside this gate. How to do it? I just apply an electrical field. So I put a lot of electrons here. Now, when I put the electrons here, electrons, they hate other electrons. So the electrons here are going to push away the electrons which are stuck here. And I'm going to get what is called a channel. So this channel, there are going to be holes here once again between the source and the drain. And now current can travel from the source and the drain. So if I apply an electrical field here, I turn this device from an open circuit to a short circuit. And if I remove the power from the gate, then again, it's an open circuit. So I'm controlling electricity using electricity. Basically, I built a switch. Okay? So there are lots of movies in YouTube. I can show you one, though. Not like a gallery of funny accents. But I was looking for one. There isn't anyone which which gives this material without digging into all sorts of part numbers that you need to order and stuff like that. But this is the field effect transistor. Now,